Hello, everyone. And as we, in our lecture, we talk about three different type of easy to implement algorithm for solving minimal cost flow problems. And the first one we introduce is the cycle canceling algorithm, which is the tutorial we're going to go over today. The second one and the third one we already presented last week is the successive shortest path algorithm. The video is already online. And also the third one is the primal and due algorithm as well as presented last Friday. So the cycle canceling algorithm, as we speak in the lectures, and has to have an initial feasible solution, primal solution to begin with, which you hear was talk about an initial feasible flow for them. And the step one is easy to find the initial feasible flow, which is we can easily using a maxima flow algorithm, such as the Edmond-Karp algorithm we implemented here to find the initial feasible solution, not necessarily optimal, but it's a primal feasible. Second, we fix the minimum cost by argumenting along the so-called negative cost cycle and using the shortest path algorithm such as the Bellman's and Ford algorithm were presented here. And there are other alternative solutions for shortest path as well. And we'll probably present it later on if I have time to put it together. But the second step is basically the biggest issue is trying to find the negative cycles. In that case, or we call it negative cost cycles and in your current solution. And then we send down the maximum possible flow along that negative cost cycle and trying to improve the current primal solution. So here we're going and the algorithm will return the maximum flow. It can be sent down to the network and the associated costs and the assignment, which is the optimal flow. Okay, and the algorithm initially assumed is a bipartite graph, but for non-bipartite graph, it's also working as well for the general minimum cost transshipment problem. So here, what you're trying to starting to present. All right. So first, we import certain library from Python, copy system, reading a CSV file, and third is the so-called time, okay, how much time it takes to execute this. The first subroutine we're going to introduce is the so-called Edmond-Karp maxima flow algorithm, which is usually standard using for solving maxima flow problem. I know we haven't talked about the maxima flow algorithms in our lecture yet, but this is one of the most popular implementation for maxima flow. And why we're here talking about maxima cardinality bipartite matrix basically is the algorithm can be used for solving regular maxima flow problem. But here we're assuming all the edges has capacity 1. And so that's why we can find out what is the best maxima cardinality matching. Okay. And this subroutine returns 3 output in a triplet. M is the dictionary of mapping member from V to U. And A is a part of the maximum matching in U. Okay. B is the part of the matching in V. Okay. Maximum matching in V. So here, this algorithm is fairly straightforward to solve. Finding a residual graph first, then we keep augmenting paths until there's no path from the source to the sink. Okay, So the algorithm is basically is successive shortest path algorithm based implementation. And again, we haven't talked about shortest path problem also, so we were going to introduce that as well to how these algorithm was put together using borrowed the functionality from each other. So admin carb algorithm, we're going to go in detail later, but here is the implementation I have. Okay, finding the maximum flow and the capacity on each one of the arc in the network, on the network, is only one. So it's basically a matching problem. It helped me to solve find an initial basic solution for the minimal cost flow problem. All right. The second subroutine is the shortest path algorithm itself, called Bellman-Ford algorithm. And the main purpose for using this algorithm is trying to detect the negative cycle for using in the cycle canceling algorithm. If no negative cycle exists, we're going to return none, and therefore the algorithm terminates. So we cannot find more cycle canceling, more negative cycle to cancel. The algorithm is also a straightforward implementation of a shortest path algorithm. We're going to come back to talk about this algorithm in detail later on, the Bellman-Ford. So here we just introduce this particular subroutine, and you can download the source code for this notebook from K-State Canvas website, and of course, and also the video for today as well. Finally is our main routine called cycle canceling routine, and we're going to first look at here using the carb algorithm for the graph we define, and to find the maximum flow, which is the initial feasible basic solution. Okay, initial feasible solution, not necessarily optimal. The second step, what we're trying to do is forming a so-called residual network. Okay, so from the current flow assignment with this initial feasible solution, we're trying to find out if what are the residual flow we can send out in on the network. It could be forward or could be backward as well. So I believe we talk about these concept in the cycle canceling lectures. Okay, so for each one of the arc flow, if it's at the upper bound, so therefore there's a reverse possible flow coming back with a negative cost. If the current flow is between 0 and the upper bound, then we have a two arc between those pair of nodes. And one is the current flow forward with a positive cost. The other one is the inverse flow and coming back with negative cost. So please refer to the detail of our lecture notes and the online video for this part. Okay, so the third part is also putting together the correct residual graph before we trying to find the negative cost cycle. So the first two part is see if there's a backward flow. If the backward flow arcs need to be established, we need to set it up. Otherwise, we just fill in the current forward flow, and that's it. Okay. After it was finished doing all the residual network, then we can call the so-called Bellman-Ford shortest path algorithm on the residual graph. Okay, on the residual graph, to figure out if there are so-called negative cost cycle. So we call this Bellman-Ford algorithm. If the cycle is not exist, I know we have the optimal solution already. and therefore we don't have to continue this algorithm. If there is a negative cycle exists, okay, then we're trying to find out the maximum flow, which is the minimum of all the forward and backward flow along that negative cycle we can send down to the cycle. So the cycle itself actually return what is the negative cycle, where they located on the receiver network. Then through that, for that cycle, for each node pair on the cycle, we're going to update our flow on the network. So first part is update the reversed edges. Okay, mostly the negative cycle created by the reverse edges to begin with, because you know the reverse flow actually has a cost of a negative cost. Okay, and then after I updated all the reverse flow, and then we can update the forward flows as well on that cycle. So this part is just update the flow based on the negative cycle. We did a manual demos on a small example, which is also presented in today's this notebook. So the flow, we find out how much flow we can send down, which is the minimum of amount allowed on the cycle. Then we update this amount, we call the flow, on each one of the reverse arc and the forward arc. Okay. So finally, is after this done, without any negative cycle can be found, then we finish the main routine and come back to print the solution. Okay, and the solution. I'm using a example we used before, and later on you can using another example we presented in the manual illustration in our lecture videos as well. So our main program is currently is reading in using the CSV reader to open the minimum cost network with a four nodes network 4 CSV, which is this example. Okay, total 1, 2, 3, 4, 8 nodes right here. Next, I want to demonstrate how the CSV file is presented. This is a CSV file, and we have right here. The first number is number of nodes on the graph in the network. Second is the node number. Node is total 10 nodes, for example, is from 0 to 9. In this example, we're assuming node 0 is the dummy source node, and node 9 is the dummy destination or sink node. So all the node 0 has a flow. So here we have total 10 node. We're adding a dummy node in front of here and taking all the node supply as the so-called upper bound on this arc to the dummy supply node. Also, I have a dummy sink node right here. And all the flow capacity from the demand node to that dummy demand node is the upper bound is 200, 200, and 300, so on and so forth. So you'll see how that actually works. So you can see that from node 0, I have the destination node from node 0 is 1, 2, 3, which is those 3. Okay. And their capacity, the second line is the capacity is 300, 300, and 100, as we have in the graph. Okay. And the third is the cost. From this dummy node to any other destination node, their cost is always 0. And next things we can see is the node 1. If you look at the node 1, the node 1 destination node is 4 and 5, and they don't have any capacity, which I'm using 9999 as their capacity. Okay, the cost from node 1 to node 4 is 2. The cost from node 1 to node 5 is 1. Similar for node 2, I can go to node 4 and node 5 without capacity constraint, and the cost from node 2 to node 4 is 1. From node 2 to node 5 is 2. Okay. For node 3 is the same thing. It's still also going to node 4 and node 5 without any upper bound, and the cost is 1 and 2 to node 4 and node 5 respectively. Finally, we look at from node 4, node 5. Okay, from node 4 can go to 6, 7, and 8 without any upper bound capacity. And these are the associated costs from node 4 to 6, 7, and 8 respectively. Node 5 is the same thing. Okay, so it's also going to node 6, 7, and 8 without any upper bound capacity and the corresponding flow cost. Okay, so here from now on, and the node 6, node 7, and node 8, they all go into one dummy demand node called node 9. Okay, so node 6 go into node 9 only with a upper bound capacity of 200, which is the node demand, and with a cost of 0. 7 is the same thing. Node 7 goes to node 9, the dummy demand node, with a capacity of 200 and with the cost of 0. Node 8 is the same thing. We're going to from node 8 to node 9 with a capacity of 300, cost of 0. Finally, the dummy demand node has nowhere to go, so it goes, you can tell it's going to node 0 with 0 capacity with 0 cost. And that also a signal to terminate the data reading process. Okay, so this is the main program I'm reading. Going through, loaded in the minimum cost flow CSV file, determining number of the vertices, which is number of node. Okay, and then read it in the range of each one of the vertices. So vertices name, I'm going to separate it by a blank space right here. For the first time, we're going to, for each one of the sink, we're reading from this. Okay, each one of the sink, which is from node 0 is 1, 2, 3. For each one of the sink, I have a loop going on, reading 3 things. The first thing is the sink index. Second is the corresponding capacity. Okay. Third one is the cost for each one of the sink. Okay. So S1 represents the sink node indexes. Sink node indexes. Okay. The C2 represent the cost capacity on that 3 arc. And finally is the weight. Weight is the cost for transporting a unit of a flow downstream. Then I'm forming that as a list. Okay, so neighborhood index, capacity list, and the cost index, list for each one of the source node to each one of the destination node. Okay, this is how we're reading the input data from a CSV format. And I have those also uploaded to K-State Canvas, and you should be able to do that. So for this particular example, the source node is 0, okay? I'm going to call the cycle canceling algorithm, giving the graph. I just built it, okay? The graph is empty, okay? Empty, there's a whole bunch of indexes, number indexes for each node, I'm sorry. Then after solving this problem, we can get it maximum flow, total cost, and transportation and inventory cost is not used in this example, so I kind of suppress their output. And for the supply chain and hub location problem, I have it for the transportation cost and inventory cost flowing on the network. So it's for a particular application, or supply chain application. So we're going to start printing solution, and you see that the solution is right here from each one of those. And I explained the solution output. But first, we're trying to find the so-called maximum flow from the source node, which is node 0, and to the destination node. Okay, and the first one is from 0 to 1, okay, from 1 to 4, from 4 to 6, and 6 to 9. Okay, second pass, which is another shortest pass, is from 0 to 1, 1 to 4, 4 to 7, and 7 to 9. The next shortest pass is from 0 to 2, 2 to 4, 4 to 7, and 7 to 9. Okay, then next one is from 0 to 2, 2 to 4, 4 to 8, 8 to 9. So this is just trying to find the initial feasible flow on the network. The last one is from 0 to 3, then 3 to 4, 4 to 8, and 8 to 9. And after we find out we cannot find any more augmenting flow to send more flow down to, so this maximum flow reaches. And then we're going to call the so-called Bellman-Ford algorithm, shortest path algorithm, trying to find out if there is a negative cycle exists. And then we find one only this time. Find one for going from 4 to 1, 1 to 5, okay? So it's kind of a backward flow. 4 send reverse flow from 4, send it back to 1. 1 going back to 5. And 5's going to 7, 7 going to 4. So 4 to 1, 1 to 5, and 5 going to 7, 7 back to 4. So this is the negative cycle we can find and this initial solution on this initial solution. And finally, we adjust the maximum flow down there. And this is the optimal flow and associated flow cost. So optimal flow is from 1 to 4, okay, is 100, and the cost is 2. And 2 to 4 as well is from 400, okay. And then from 3 to 4 is 100. 1 to 5 is 200. 4 to 6 is 200. And 5 to 7 is 200. 4 to 8 is also 300. So the total cost is 1,500. This is consistent with the previous several algorithms we solved exactly the same example. Okay. Continue talking about a different example. This example we illustrated in the lectures videos, and this is another example with the 4 nodes only, and with the source node connected, dummy source node connected to the only supply nodes right here, node 1, and dummy destination nodes, okay, and connected these two, node 2 and node 4 has the node demand 3 or 6. So total supply is 9, total demand is 9 as well. So we're going to start solving this problem. 8 over here, the first number represents the upper bound on the arc. Second number 2 represent the cost, and so on and so forth across this network. And we're using the graph3.csv file right here and trying to solve it and see if we can find out. All right. So this algorithm is this example we presented called graph3.csv file. After reading it, the solution procedure like this. First, they find out 4 separate successive shortest paths to build the initial feasible flow on the network. Okay, initial feasible flow on the network. Okay, so the first one is from 0 to 1, to 1 to 2, 2 to 5. So this is 0 to 1, 1 to 2, 2 to 5, and satisfy this node demand at the node 2 of -3. The second shortest path we find out is 0 to 1, 1 to 2, 2 to 4, 4 to 5. Okay, second one is 0 to 1, 1 to 2, 2 to 4, 4 to 5. Okay, so this is this part, satisfying part of a node demand for node 4 of 6. Okay, which is 3, I think. The third shortest path is from 0 to 1, 1 to 3, 3 to 4, 4 to 5. So 1, 2, 3. Okay. So the next one is from 0 to 1, 1 to 3, 3 to 4, 4 to 5. All right. And the last shortest path is 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, basically, is from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. So we find out actually total of 4 shortest paths sending down. This is very much like the successive shortest path problem. However, we didn't take care of the minimum cost. So this is the initial feasible flow, but see if we can find any negative cycle and to improve the current solution. And the first negative cycle we find now is 2 to 1, 1 to 3, 3 to 4, 4 to 2. Okay, let's look at this. So 2, 1, 1, 3, 2 to 1, 1 to 3, 3 to 4, 4 to 2. So this cycle. Okay, first. And we have this exact example showing them in our lecture video and do it manually. The second negative cycle is 4 to 2, 2 to 3, 3 to 4. Let's look at this. So this is the negative cycle we have. Okay, this is the negative cycle we have. And therefore, we can send down to 2 down to that range. So after that, there's no more negative cycle exists. And the optimal flow is 1 to 2 equals to 7, 1 to 3 equal to 2, 2 to 3 equals to 3, 2 to 4 equals to 1, and 3 to 4 equals to 5. And total cost is 29. Okay, so this is only take 3.5 milliseconds. Actually, could be less, much less. So this solution exists exactly the same as our cycle canceling algorithm presented in our lecture notes and the lecture video. So I'm using 2 examples, okay, to demonstrate this correctness of this minimum cost flow cycle canceling algorithm. And pretty much we illustrated all 3 algorithms in the Python implementation. Hopefully this will help you understand the algorithm we presented in the lecture. Okay, we see you in the next lecture video. Bye-bye.